Okay, so now we'll do the proof for the factorization criteria for the discrete case. So suppose that, so we have to do two ways, right? So first is we suppose that T of Y is sufficient for theta, and we must show the factorization exists. So then discrete case. And here's where we kind of a strange thing to do, but we just will augment this, and this doesn't hurt anything. And this is redundant, but we're trying to show something. So maybe this is the right thing to do. So this is certainly true. And now I have this joint distribution, which I can write as the product of a conditional distribution and a marginal distribution. So this is equal to right. And since T of Y is sufficient, this is, well, they're in the other order I usually write it, but this is not a function of theta. So this is a general function. It could involve any kind of form of the observations of the sample. But this, clearly this is, the only inputs here are T of Y, not Y itself. So this is a function of T of Y. And because yeah, and this, and possibly the probably the certainly the parameter. Yeah. Okay, so we showed the factorization exists. Sorry about that if I sounded confused. Yeah, so I think this is good. Okay, so we showed that if T of Y is sufficient, go through here, and we get this factorization, and this is not a function of theta because T of Y is sufficient, and this in general is a function of theta, and as well it's a function of this T of little y. That's all that it's a function of. Okay, so let's go the other way now. So suppose the factorization exists. So suppose factorization exists. So suppose factorization exists. Can we just write that? Yeah. Okay, well then we have to show that the conditional distribution of y given T of y does not depend on theta. So we have probability okay, so let's write what it is. So again, I can take out the condition. Maybe I should write it once. but now I can take this out, right? Since it's doesn't add anything. It's contained in this first part. So so we're here now. But the factorization exists. But maybe first we should talk about what this should be, right? So if I want the probability that some function of the capital Y is equal to some number, right? This is just some number once T is or a vector, but probably, yeah, number of vector. And once T is defined, this is just, we just want to sum up the probabilities of all Y's, because this is a discrete variable too. So I just want to sum along all Y's where this function of the Y would give me this number, right? That's what the bottom says. So this is equal to probability Y equals this particular little y divided by a sum over, let's say, all little x, such that t of little x equals t of little y. And in here, I want the probability t of, sorry, I want the probability y equals x, right? Yes, probability y equals x. Yep. Okay, well, what's this? This is, let's write this one more time. Y equals little y. And on the bottom, I'm summing over all little x, where t of little x is equal to this number, t of little y. And I want, yeah, I want the probability y equals little x again. So here's where I should go to the hypothesis of the proof here. We are assuming the factorization exists. So we're going to put this in now. So here I will write g of t of y, little y, theta, times h of little y. And here I will write g of t of little x, right? So probability y equals little x. So it's g t of little x theta times h of little x. But since t of little x is equal to t of little y, I can replace this, of course, when I'm in this sum with t of little y. So this is equal to g. My writing is getting sloppy as I go here. So theta. And then divide by the sum here. I'm replacing this by little y in here. So and this is the sum over all x such that t of little x equals t of little y. And I could take this, certainly take this outside of the sum because it doesn't depend on the sum. This is hitting every single h of x. So I can just take it out and you see it will cancel here. So I get h of little y and I'm dividing that by the sum. Which doesn't depend on. So you're done. if you like, think about the Bernoulli case, right? Where we had 1 over n choose the sum of yi, right? So in the Bernoulli case, we had something like 1 over n choose sum yi. And this is really the total number of sequences, Bernoulli sequences that summed up to this particular number, sum of little yi, in a sample of n, right? This is n choose that number, so it was how many different sequences have this sum, and the probability that we're at any one particular one, they're all equally likely, was just 1 over that. So here you see this is just the this is what you get. Okay, so a piece canceled. I'm not saying it's the exact probability. It canceled up here and here, and you sort of have a count. Yeah, this is the count part of the binomial. You could think of your binomial, right, as probability of any sequence times the number of those sequences, the n choose k part, that's the number. And so that's what you're left with. Those two, the other two things cancel because the probabilities are the same. So this is the same as this in this case. So yes, not a function of theta, and the proof is complete in the discrete case. So just a little more on this, which is kind of extending into the next section, which is that yeah, I don't know, maybe should do a separate thing. Yeah, I think that'll just be the proof, and then we'll stop and do a separate thing for the next one.